Welcome to the Deep Dive. We've got some great material today, sent in by you, our listener. It's excerpts from key considerations for choosing the right IoT antenna.
Yeah, it's a really good piece. Antennas, they're not flashy, maybe.
Not usually the first thing you think of with IoT,
Yeah.
right? But they're, well, absolutely essential.
Mm-hmm.
Think about it, smart cities, your smart home, all that communication. It really relies on this tiny, often invisible component.
It does. The source calls them the unsung hero of IoT connectivity, and I think that's spot on.
Totally agree. So our mission today is pretty clear. Unpack these key factors for picking the right antenna, give everyone a solid grasp of what matters.
Right, because get it wrong and the whole system can just, well, fall flat. It's not just a minor detail.
Okay, let's dive in then. The material makes it super clear. Antennas send and receive the RF signals. They're the link.
They are the link. And if that link is weak or wrong...
You get connection problems, performance tanks, the whole network just doesn't work efficiently. It's like having super fast internet but using dial-up modem thinking.
Yeah, exactly. Or a really old, slow computer, the bottleneck. And the consequences aren't trivial.
No.
It could be annoying, like your smart speaker not responding, or it could be critical think industrial controls or, medical devices. Data loss there is serious.
Definitely. So this small part has a huge impact on whether an IoT project actually succeeds.
Absolutely.
So where do we start if we want to get it right? The first big one seems to be frequency range and bandwidth. Sounds technical, but...
It's basically making sure everything's speaking the same language wirelessly.
Right.
The article lays it out. Different tech uses different bands. You've got LoRaWAN way down in the sub-gigahertz range, like 868 megahertz in Europe or 915 in North America. Good for long range, low power.
Okay.
Then you have cellular IoT, like LTE-M, NB-IoT. They're up higher, maybe 700 to 2100 megahertz. Much higher frequencies.
So it's like tuning a radio. You need the antenna tuned to the right station, the right frequency your device is broadcasting on.
Precisely. If you're using LoRaWAN for, say, farming sensors across acres.
You need that specific sub-gigahertz antenna.
Exactly. You can't just slap on something meant for, I don't know, a 5G connected car. It won't pick up the signal properly, if at all.
Makes total sense. And the article mentions multi-band antennas.
Ah, yes. Those are really interesting. They offer flexibility, an antenna that can handle multiple frequency ranges.
So if your device needs to switch between networks, maybe cellular and something else?
Or if you're designing something and aren't sure exactly which network it'll end up on or want it to work globally, it's like a universal remote for frequencies. Really handy.
Okay, so frequency first. Got it. Next up is range and coverage. This feels a bit more intuitive. How far does the signal need to go?
Pretty much. The physical distance between your device and whatever it's talking to another device, a gateway that dictates your needs.
Like the examples they give.
Right.
Big smart city projects or sprawling industrial sites.
Yeah, sensors miles apart sometimes. You absolutely need long-range antennas there, often those LPWAN types we just mentioned. They're built for distance.
Right, the low-power, wide-area networks. They sip power, but reach far.
But then, if you're just connecting things inside your house, like smart plugs or lights...
You don't need an antenna that can beam a signal across town. Something smaller, shorter range is fine.
Exactly. You need to understand the actual area, the footprint you need to cover. Don't buy more range than you need, but definitely don't end up with dead spots because you underestimated.
Okay, that makes sense. Now, what about the physical shape and size, the form factor? The article talks about a few main types. First, embedded.
Yeah, embedded antennas. They're built right into the device itself.
So perfect for things like smartwatches or small sensors where space is really tight.
Totally. They're great for making devices sleek and compact. The trade-off, though, is that being small and inside the casing can sometimes limit their performance a bit compared to...
The next type, external antennas, the ones you see sticking out.
Exactly. The article flags these as better for outdoor use or tough industrial settings. You generally get better range and performance.
And you can position them better, right? Like mounting one up high for a clear signal path.
Precisely. Being external gives designers more freedom with size and design, which usually means better gain, better signal quality, especially if there are walls or metal nearby.
Okay. And the third one mentioned is PCB antennas, printed circuit board.
These are actually etched directly onto the circuit board itself.
Wow, okay. So super integrated.
Yeah, very cost-effective, saves a lot of space. You see them all the time in IoT modules where keeping costs down and size small is key. Maybe not the absolute peak performance of a big external one, but often more than good enough.
Very practical. Okay, moving on. the environment. This seems huge. Key consideration in 4, it's not just about empty space, is it?
Not at all. The real world gets in the way. The article points out temperature, humidity, physical stuff like walls, metal structures, they all mess with radio signals.
Right, so an antenna that works perfectly in a lab might struggle outdoors in the rain or inside a factory.
Absolutely. Think extreme heat, freezing cold, moisture, or just thick concrete walls. They can absorb or reflect the signal.
Which is why the text mentions ruggedized antennas for those tougher spots.
Exactly. Built to take a beating physically, but also designed with materials that keep working reliably despite temperature swings or dampness. You need that reliability for industrial or long-term outdoor deployments.
Makes sense. Now let's tackle gain and efficiency. A bit more technical, maybe? Gain, measured in dBi. The article says it's about focusing energy.
Yeah, think of it like the beam of a flashlight. Higher gain means a tighter, more focused beam.
So it travels further in that specific direction.
Right. Great for long-distance point-to-point links, but the beam is narrow, so the overall coverage angle is smaller.
And lower gain is the opposite, more like a bare light bulb.
Kind of, yeah. It spreads the signal out more widely, 360 degrees maybe, but not as far in any single direction. It's always a trade-off, focus versus width.
Okay, and efficiency. How well the antenna turns electrical power into radio waves.
This is super important, especially for battery-powered IoT devices.
Because you don't want to waste precious battery power just making the antenna warm.
Exactly. Every bit of power counts. A high-efficiency antenna means more of that power actually goes into sending the signal, less is lost as heat.
Which means longer battery life, huge for deploy and forget type sensors.
Absolutely critical. It impacts maintenance schedules, overall cost, everything.
Okay, great.